In Florida, there's a special lab studying lightning. ABC's Bill Blakemore went to pay a visit.
At any one moment, there are about 2,000 electrical storms on our planet. It's a constantly crackling ball of lightning, about 100 volts a second, striking people, houses, power lines, airplanes.
Normal commercial plane about twice a year.
All right, so it's twice a year. Normal commercial airplane getting hit by lightning. Twice a year. And you're perfectly safe while you're on the inside, right? So the question is why?
In Glenview, high winds took down a power line, trapping a woman inside her car. Police did not know if the wire was live, so they ordered the woman to stay inside the car to avoid contact with the ground. Then they shut down the entire intersection. The driver was trapped for nearly 2 hours until ComEd crews showed up.
I called the fire department and told her to stay in the car and not to move and not to attempt to get out of the car. So
How was she handling this?
Well, at first she was crying and she was pretty hysterical, and she was talking to family members on her cell phone.
ComEd crews eventually shut off the power, and the woman was allowed out of her car. The driver was a bit shaken, but she is said to be okay.
Most people think that she's safe because of the rubber tires. This is a common misconception. Rubber tires really don't have anything to do with what's going on here. Remember, this is a live wire going up, touching the metal casing of the car, and then coming down and touching the ground, guys. This is a complete circuit. This car is part of the circuit already. This car is much of the part of the circuit as a guy who's being electrocuted on the electric chair. All right? It doesn't matter that the guy on the electric chair is wearing rubber shoes. It doesn't matter because it's part of the circuit. Current is going to go through it. In this case, the current is going through the car. This car is completely electrified. So the question is, why is it that she's not getting shot? All right, so Ian,
more conductive.
I'm sorry, Ian, what would you say?
Because the metal is more conductive.
Because the metal is more conductive. Some of you guys will claim, and I know what you guys will claim because I've been doing this stuff for almost 15 years. The part of the reason a lot of you guys think that she's safe on the inside is because she's not touching any metal on the inside. She can touch all the metal on the inside. It makes no difference. Forget about touching the metal. She can lick the metal if she wants to. Imagine that she's got a metal fetish, right? She's going to go, I lick the metal. It makes no difference. She can touch the metal on the inside. She's going to be fine. She can touch the outside metal. She's still going to be fine. All right, so why is it that she's going to be fine if she's touching the metal on the inside?
Come on, please help me out. Yes, we'll carry you. Hold on. I got struck by lightning. Yes. How about that happen?
In August 2003, Matt Thompson was hit by lightning in the hills outside Keystone, Colorado.
A bolt of lightning taken straight in the chest.
What you say? Don't I know it?
The direct hit traveled all the way through Matt's body.
I had no clue what happened.
Matt's story was big news. On websites worldwide, the issue was raging.
Hey, you almost died.
Was Matt's metal tongue stud the reason he was struck?
So my tongue ring.
I don't know, dude. You might have swallowed it.
Let me see. Where's your tongue? Let's see it. Oh, it's broken off in there, it looks like.
Body jewelry attracting lightning strikes?
So does metal on your body attract lightning? What do you guys think?
No, because there's more resistance between you and the metal than it would ever care about. Like, it would never get to that point. Your body's the limiting factor in the resistance.
Okay, so Matthew, I'm going to give you 5 points for it. So what you're saying is your body is a lot more resistant.
Yeah.
Electricity. So unless the metal is the one that's taking a hit, it's not going to make that much of a difference. All right, that's one way of looking at it. What else? Does metal on your body attract lightning? Like coins in your pocket, earrings, tongue rings, lightning rods. Are they made up of metal, plastic, wood?
Metal.
They're made up of
Metal.
Metal, right? Okay, what's the purpose of a lightning rod? The purpose of a lightning rod is to attract lightning, right?
Right.
So if that's the purpose, what do you think works better? Is it metal or is it wood or is it porcelain?
It's metal, but it's got to be grounded.
All right, so does metal attract lightning, yes or no?
No.
Ian, I think I have to kind of beat you up a little bit. You're digging in. Does metal attract lightning? What do you guys think? It needs to be grounded. So if the metal is up in the air like an airplane, it would never get struck by lightning, right?
Fuck.
Did I just give you an answer?
That doesn't.
All right, so the metal itself, does it attract lightning? Let's talk about Gauss, man. Let's talk about Gauss. What did he do? Gauss made life easy. How so? And the equation that we came up with for the previous case right at the surface state will be the same. Guys, that's 2 pages of work. 2 pages of work. Now, what Gauss did, he came up with a better way of solving this problem. In fact, his solution is so simple and so elegant. That's the reason why we're going to be talking about Gauss. We're going to make life easier for us. Instead of using a lot of fancy calculus, we're going to end up using right, so he's a German mathematician. One of Einstein's heroes. Obviously, in Germany, he's so well recognized that you can see his picture on their currency. So what he did, basically, he's going to give us the Gauss's law. And so what is the Gauss's law? How does it work? Okay, ignore that one. Gauss's law is going to work on the principle of flux. So what is flux? All right, so what is flux? flux means flow. All right, what's flowing in this case is the electric field through some kind of surface area. So the definition of flux is the amount of electricity flowing through something. All right, so flux means flow. All right, so here's the surface area. All right, so area is represented as an area vector that you're looking at here. And this is the amount of electric field which is going to be intercepted by that area. All right, so this is the electric field flowing through this area is known as the flux. All right, the symbol that you're looking at. This is the Greek letter phi, or Greek letter F, more like F or phi. I don't care how you say it. This simply represents flux. So flux in this case is the amount of electric field which is going to be intercepted by some kind of a cross-sectional area. This represents the amount of electric field going through a surface area. So the amount of electric field being intercepted by a surface area. This is a dot product, something we will discuss shortly, so it's not a big deal. So the only thing I want you to know is the meaning of flux that represents the amount of electric field flowing through this area, or the amount of electric field which is being intercepted by this area. So that's it. Now, here's what Gauss came up with. According to Gauss, the amount of electric field which is going to be intercepted by this area is going to be dependent on the net charge on the inside of a Gaussian enclosure. All right, that's the meaning of it. So the flux depends on the amount of charge, net charge, within the Gaussian enclosure. Move forward so that you guys have an idea. Here's what I'm talking about. This is a Gaussian enclosure that you guys are looking at. It could be a sphere, it could be an area. In this case, it's a spherical region that you're looking at. So the flux in this case is represented by the amount of electric field, which is going to be intercepted by this enclosure that you're looking at. All right, so the flux in this case, the amount of electricity intercepted by the area of this enclosure is going to depend on the net charge on the inside, divided by some kind of a constant, but don't worry about the constant. So the flux depends on the net charge on the inside of a Gaussian enclosure. All right, so that's the meaning of it. Now, flux could be positive. Flux could be positive, it could be negative, it could be zero, and so forth. So let's talk about that. If the net charge on the inside is positive, in this case it is positive, this charge is positive, this is going to give you a positive flux. Positive flux is going to be an outflux or outflow that you're looking at. All right, so if the net charge on the inside is positive, then the flux is going to be positive. Let's say you end up getting yourself a positive flux. If the net charge on the inside is negative, it's going to give you a negative flux. Net charge is negative, it's going to give you a negative flux. All right. Now, this region that you're looking at is your Gaussian region. Guys, what is the net charge on the inside in this case? Notice that you have a negative charge and you have a positive charge. So if you have an equal positive and negative charges, what's the net charge on the inside? It's going to be zero, right? Zero. Because despite the fact that you have charges on the inside, the net charge on the inside is going to be zero. One of the things that I need you to notice, because flux is flow, that's the amount of flow being intercepted by the Gaussian surface. Notice that these are incoming electric field lines. Number of incoming electric field lines and the number of outgoing electric field lines will be equal to each other. All right, so the strength of the electric field intercepted by the surface of the enclosure is going to be the same for the incoming electric field lines as well as the outgoing electric field. All right, so that's the meaning. So in this case, net flux is going to be zero because the net charge on the inside is going to be zero. You have equal number of positive and negative charge. All right, here's your Gaussian region, and notice that the net charge is on the outside. All right, every time you're using this formula, guys, you're only interested in the net charge on the inside. What is the net charge on the inside? There's no net charge on the inside. If there's no net charge on the inside, the flux is going to be zero. All right, so this is the game that we will get to play. So the guy who came up with it is Gauss. And simply put, he's talking about flux. Flux represents the amount of electric field which is going to be intercepted by a Gaussian surface. That's it. So the amount of electric field intercepted by the Gaussian surface is only going to depend on the net charge on the inside. All right, so that's it. You guys are looking at the formula. This is the Gauss Law. So flux is F or phi on the side. Flux depends on the net charge on the inside. Epsilon naught is your constant, so just keep it there. How we come up with it is something that we will discuss shortly. By definition, flux represents the amount of electric field intercepted by the area of the Gaussian enclosure. So that's what it represents. So what is flux? Simply put, flux is the amount of electric field being intercepted by the area of the Gaussian enclosure. All right, so next question, what causes flux? What causes flux is the net charge on the inside. All right, so net charge inside, so cause of flux is located right here. So that is the net charge within the enclosure, the Gaussian enclosure. You guys understand that the Gaussian enclosure is just an imaginary region, right? So understand that it's an imaginary region, something that you draw around a certain region that you're looking at. So the cause of the flux is going to be net charge on the inside of the Gaussian region. If our net charge resides outside, what's the strength of the electric field within the Gaussian region? If the net charge resides outside, what is the electric field within the Gaussian region?
Zero.
it's going to be 0, right? So if your net charge, if there's no net charge on the inside, or if the net charge resides outside, then the electric field within the Gaussian region is going to be 0. Question number 4: what's the net electric field inside the Gaussian surface? There's an equal number of positive and negative charges on the inside. So if you have equal number of positive and negative charges on the inside, the net charge on the inside is going to be
0.
Very good. That's it. All right. So S1, this is one of the imaginary Gaussian surfaces. S3 is the second one. All right. This is the second one. This is the third one, and so forth. All right. So now we can have a conceptual discussion. All right. So here's your Okay. So here's your Gaussian surface. Is this a positive flux, negative flux, or no flux?
Positive.
It's positive flux, right? All right. So net charge on the inside is positive. So through this surface that you're looking at, this is going to give you a positive flux. Positive flux, negative flux, or no flux?
Negative.
This is a negative flux. So everything is, if there's an inflow, there's an outflow here. All right. Region number 3. Positive flux, negative flux, or no flux?
No flux.
No flux, because the number of lines entering and leaving this region will be equal to each other. Also, the net charge on the inside is going to be 0. All right. The 4th region that we're looking at is the entire enclosure here. Okay, that's 4. All right. So is this a positive flux, negative flux, or no flux?
No flux.
It's going to be no flux because the net charge on the inside will be 0. Okay. No. Okay, so let's focus on this one. The other one is a little bit too simplistic. Okay, we'll do this problem, but we're not going to use numbers. I don't care much for numbers for these kind of problems because it's a waste of time. It's something conceptually we can do that's real fast. So let's study this, take all the time we need. I'll give you guys one more second. All right, time's up. All right, so you got 2 Gaussian regions. This is one of them. This is the second one. Okay, take a look at the first region. Is this, what's the net flux? Is it positive or negative within this region? It's going to be positive. It's going to have positive net charge, right? All right, so having said that, now let's go back to the second one. Here's the second region. So the net flux, do you think it's going to be positive or is it going to be negative? Well, imagine that all the charges have equal magnitude.
It's negative.
It's going to be negative, right? If all of them have the same magnitude, so you have more negative charges than the positive charges. So the net charge is going to be negative. So which means that we're going to end up getting a negative flux, which means that the more electric field lines will be entering the region than leaving. That's it. All right. And you can do it numerically. It's the same idea. All right. It's a waste of time, basically. So it's more of a conceptual exercise. All right, so our topic is the Gauss Law. All right, so let me make a summary statement regarding this, and then provide some explanations. Gauss's law is related to the electric strength generated by a net charge. So when you have a net charge like this, if it's a positive net charge, obviously it's going to generate the electric field. All right, so this is your cube. According to Gauss, what you need to do is you need to come up with some kind of an imaginary Gaussian region. All right, so this is your Gaussian surface that you're looking at. The amount of electric field intercepted by this area is going to give you your flux. That's what it means. And your flux depends on the net charge inside the Gaussian surface. That's the meaning of it. So, strength of the electric field intercepted by the area of the Gaussian surface is going to be your flux. Electric field is a vector that you're looking at. In this case, it's a radial vector. This is your Gaussian surface. And notice that right at this point, it's got an area pointing in this direction. Right at this point, the area vector is going to point in the same direction, right? Okay, so the area is going to have a size, it's going to have a direction as well. Discuss the meaning of, there's a point here, right? This point is called a dot. And dot looks like this. All right, if you've never seen a dot before, let me show you. All right, this is what a dot looks like. All right, you can put an A here, and then you put a B here. What does that represent? It's called the dot. Yeah, whatever that is, we have to kind of touch on it. Okay. All right, so this is your Gaussian surface. All right, now let's take a look at what happens to this equation. Do you guys notice that there is an integral sign, and in the middle of the integral sign, you have this circle, and then this circle has a direction in the counterclockwise direction. So what it's saying is, when you're integrating the surface area, you need to integrate everything in this direction, in the counterclockwise direction. Okay, so the mathematics, there's a little bit more information built into the math in this case. So here's the strength of the electric field, and here's your surface area, differential surface area that you're looking at. Now, there's an underlying assumption here, without even mentioning it, I'm assuming that the area vector and the electric field vectors are in the same direction. Whatever that means, you will notice it shortly. So I got rid of my, my arrows on top. Net charge on the inside is going to give you this. All right. Now, Gauss's law works for smooth, nice, symmetric distribution patterns. So the area that you're looking at, if this is for a sphere, you don't need to do the integral, because if it's a sphere, you know what the area of a sphere is, right? What is the area of a sphere? Area of a sphere is 4
thirds pi r cubed.
R. All right, there's
Cubed.
inflation, right? So I have to kind of go from a cube to a square. Is that right? There, that's what you end up using. This is the area of a sphere. All right, nice geometry that you can come up with. If it says cylinder, what do we use? Area of a cylinder. So this is R. I'm going to use L for this one. So what do we do for this one? Area of a cylinder. It's going to be pi r squared. Something like that. So for an area of a cylinder, what do we need? You need that perimeter. You need the circumference times L, right? Circumference times L is going to be the area of that containment. So it's going to be pi. There's a 2 pi r times h. But before we move any further, I just want to talk about the dot product just briefly. So what does the dot product represent mathematically? All right, so the dot product represents the following. Imagine that you have one vector pointing in this direction. Okay. And then imagine that there's a second vector pointing in a different direction, which is going to be b. If you're looking at the dot product of A and B, this is known as a dot product. So a lot of you guys, it looks like a multiplication. It's not. What this means is you'll be interested in the component of A along the direction of B. That's what it means. All right, so this would be the component of A along the direction of B in essence, which is going to be multiplied by B. All right, so you're looking at the component of A along the direction of B. How much of A is going to be along the direction of B, contributing to the value of B, or the multiplication, which means that there would be some kind of an angle in between. The angle is going to be theta in this case. So you're looking at the component of A along the direction of B. So the component of A along the direction of B is going to be cosine A, right? Does that make sense? So you're looking at the contribution of A to B in essence. Okay, how much does A contribute to B? Expressed as a dot product. So it's not A times B, it's a fraction of A along the direction of B, contributing to whatever B is doing. All right. So this is known as the dot product. This is something that you will study in Calc 3 if you've studied it. Obviously, I'm giving you an oversimplified interpretation of it, but this is a big deal in physics. The dot product is something that we get to use. All right, so this is your aside. All right, so this is your aside from Calc. How does that work in physics? It works in physics just fine. All right, so imagine that you got your electric field in this direction. So the electric field happens to be pointing in this direction within this region, except the area. The intercepting area is pointing in a little bit different direction. All right, so I'm just going to come up with some kind of an area here. All right, so this is the area that's going to be intercepting the electric field. All right, so the electric field. Notice that the area is not oriented in the same direction. So the area vector is actually oriented in this direction. All right, so there's going to be an angle in between there. This is the angle. So what I'm interested in is the amount of electricity, the component of electricity in the direction of the area vector. That's what it means. Notice that 100% of the electric field is pointing in this direction. I'm only interested in the component of this along this direction. So the component of the electric field along the direction of the area vector is going to be actually small, right? The larger the angle is, the smaller the portion of the electric field pointing in this direction. So that's what the meaning of the flux is. So the flux is going to be represented in terms of the dot product of the electric field pointing in the direction of the area vector. So that's the component of the electric field intercepted by the area is going to give you the flux, and which depends on the net charge inside the enclosure, and whatever that enclosure is, you're looking at a single surface. All right, so when we actually write this out, it's going to look like this. And then if I were to rewrite this, it's going to look like this. So this is the electric field intercepted by the area of the enclosure, which can be expressed in terms of the angle. Depends on the net charge on the inside. Okay, so this is everything expressed in terms of the vector form using a dot product, and this is the expression in terms of the scale. Okay, so how do we know that the Earth is negatively charged? Here's how we know. Here's the Earth. It looks flat because it is dimensionally. The reason why we know that the Earth is negatively charged is because if you can measure the strength of the electric field, it's pointing in the downward. Right, so the Earth's electric field points towards the Earth, which means that the Earth is negatively charged. So the question is, what is the value of that charge? So it's 150 newtons per coulomb directed towards the Earth. So what is the net charge of the Earth? So this is problem number 3 from the handout. All right, so it's going to be, what is it, 150 newtons per coulomb? That's it. So the question is, what is the value of the Earth's magnetic electric field in terms of coulomb? What you need to do is you need to use the Gauss Law. The best thing to do is just place your Gaussian surface right where the surface of the Earth is. So this is your Gaussian. And look at the net charge inside. And we know that the net charge inside is going to be negative because the electric field always points towards the negative charges. All right, so that's our Gaussian surface. Speaking of that being the Gaussian surface, this thing is spherical. And this is the radius that we're looking at. All right, so our Gaussian surface is spherical. All right, so now we can figure out the net charge. Write out the Gauss Law. So here's your flux. Here's the strength of the electric field intercepted by this area. Here's the net charge on the inside. All right, guys, here's the electric field. And you notice that the area vector is going to be parallel to it at that point. You're going to be looking at this region. All right, so you have E, EA, E, EA, times the cosine of the angle in between. Okay, given the fact that they're pointing in opposite directions, what is the angle in between? What is that angle? This angle that you're looking at is going to be, what is it? 180 degrees, right? So if that's the case, what is cosine of 180 degrees? It's going to be what? Yeah, that's all right. Strength of the electric field is going to be constant. All right, so here's your area vector. So because of the fact that the angle is going to be 180 degrees, you end up getting a negative. So this first sphere, all right, so what do we know about the sphere? Okay, area of a sphere is going to be 4 pi r squared. Okay, so now let's do a back substitution. So this is going to look like 4 pi r squared times E. You got your negative charge. Solve for the charge itself. All right, so when you solve for the charge itself, this is what you end up getting. All right. This is the final answer. And obviously there's going to be a negative up front, so it's going to be a negative charge. All right, so before we put the numbers in, let's check to see what we got in terms of the numbers. All right, so we got the value of E. Obviously, we have the value for epsilon naught, and we got the value for pi. We know what R is. Okay, guys, R is the radius of the Earth in this case. All right, that's something that you look up. Radius of the Earth, I'm guessing that it's going to be 6.38 times 10 to the 6. I think this is the average radius of the Earth. So that's the value that you get to use. And then plug the numbers in. All right, so it's going to be negative 6.75 times 10 to the 5th. 675,000 coulombs is what we end up getting. That's it. Okay, this thing is charging up. Let's move on to something a bit more interesting. So Earth is negatively charged. So the question is why? I have no idea. That would be something interesting to investigate. So Earth is negatively charged. Airplane is getting struck by lightning.
Fuel cell lights and AC bus light. Fuel cell disconnect. AC bus overload 1 and 2.
As Apollo disappeared beyond the clouds, Commander Pete Conrad reported catastrophic failures with the electrical systems.
Yeah, the problem here. I don't know what happened. I'm not sure you get hit by lightning.
Conrad was was right. These photographs revealed that it was struck, not once, but twice, by lightning that came seemingly from nowhere. Quick thinking by Mission Control helped them restore power, but it was a close call.
We've had a couple of cardiac arrests down here too, Lee. I think we need to do a little more all-weather testing. Amen.
It was a problem that needed urgent attention. NASA dispatched test pilots to seek out thunderstorms. Their missions took them through turbulence and hailstones, which could tear a jumbo jet apart.
It's one of the very early strikes that we had, where it struck the nose boom, as many of our lightning strikes did, and it then swept up over the top of the windshield, down that metal bar that was over the top of our heads in the canopy. And I could just happen to look up, and I could see helical chunks of plasma as the lightning channel broke apart as it flew back over the top of my head.
The onboard camera revealed something totally unexpected. The plane wasn't just intercepting lightning, it was actually triggering it by interfering with the electrical field inside the cloud. As Apollo 12 flew through the cloud of charged ice particles, it left a wake of hot ionized gases and conductive contaminants. The exhaust became a huge streamer, and the burning rocket plasma a giant lightning rod.
Okay, so why is it safe inside a conductor? A conducting enclosure like the Faraday's. One lightning strikes, it's going to deposit like charges onto the metal surface. In this case, the negative charges are being deposited. So the struck is going to transfer negative charges to the metal surface. When you have like charges, what do like charges do? They repel each other, right? They're going to try to get away from each other as far away as possible. What is the furthest that they could get on a metal? It's going to be the surface. So all the like charges will be repelled to the surface immediately. As a result, the net charge is going to remain on the top. So all the net charge itself, excess charge, is going to get repelled to the surface. All right, when the net charge is repelled to the surface, what's the strength of the electric field inside the enclosure? Right, so guys, imagine that this is your metal itself, right? Okay, so this is your metal itself. And now what's going to happen is the lightning is going to deposit negative charges on it. All right, so the lightning is coming in, and notice that the negative charges are being deposited. So these negative charges will reside right at the surface. So negative charges will get distributed onto the surface that you're looking at. So what is the net charge on the inside? So the thing to do is you need to just take your Gaussian surface, and then you will have to place your Gaussian surface right where the surface is, like right inside of the surface. That's what I'm doing. All right, so the green is going to be our Gaussian surface. All right, this is your Gaussian. What is the net charge on the inside? So the net charge is going to be on the outside. So the outside charge is going to be negative. All right, so the charge is going to be outside is going to be negative charge. So net charge, excess charge is going to be outside. What is the net charge on the inside, if that's the case? All right, so the inside charge is going to be 0. Net charge on the inside is going to be 0. If the net charge on the inside is 0, what happens? If this is 0, area is not 0, which means that the electric field on the inside is going to be 0. All right, so strength of the electric field intercepted by this area, this is your total area. All right, so solve for the strength of the electric field on the inside. This is the net charge on the inside. And the net charge on the inside is 0. If the net charge on the inside is 0, the electric field on the inside is going to be 0. All right, so which means that the electric field on the inside is going to be 0. Electric field is what drives the charges across a region. Electric field is what drives the charges across your body. If the electric field on the inside is 0, you're perfectly safe. You're not going to get shocked. You can touch the inside of the metal. There's no electric field on the inside. You can touch it with both hands. You can put your face next to it. It makes no difference. You're not going to get shocked because there's no electric field on the inside. All right, so the like charges, when deposited onto a metal surface, a metal enclosure, in general, they will be repelled to the surface, and then they will get repelled away as far away from each other as possible. The furthest that they could get without leaving the structure is going to be strips of that structure. And on the inside of the enclosure, you're going to be perfectly safe because the net charge on the inside is going to be 0, which means that there's no electric field on the inside, forcing the charges to go through your body. That's the reason why you would be safe inside a metallic enclosure, otherwise known as a Faraday cage. Examples of Faraday cage: you got your car, obviously you got an airplane, and every single sensitive electronics is going to be enclosed inside a metallic Faraday cage, like your computer is going to be housed inside on purpose. All right, so here's a car. He's getting struck by artificial lightning. You got a spark generator in there. Notice that the tires don't help. It's going to go right through the tire. So as long as you remain on the inside, you're going to be perfectly safe.
If you can't do that, you should get into a metal car.
The car's metal body discharges the current away from the driver and to it.
True or false? You can be electrocuted by lightning in your car.
True or false?
False.
It's going to be 100% false. All right. The answer is false. You cannot be electrocuted by lightning in your car. It's out of the question. Conditionally. provided that you got your windows up.
The answer is true.
So answer is true, Edmund. So that got my attention. According to physics, you're perfectly safe. And they're claiming that, nope, you can't be struck by lightning inside a car. Of course, as soon as I was watching this, I got all excited because I want to see the evidence of physics being wrong. Okay, that's the sort of stuff that gets you excited if you're a physicist, which means that there's something wrong with physics, which means that you can do research on it. So I'm looking forward to actually seeing the evidence of someone getting fried.
Watch. You're about to see actual video of what it would look and feel like if it happened to you.
All right, so the car gets struck. The guy's screaming, but he seems to be okay.
Oh my God!
The windshield wipers are working, which means that the electrical system wiring is okay.
The car was just struck by
the engine is still running, so the engine is okay.
lightning! Oh my God!
This young
Oh, I'm looking at the clock. The electronics is okay. So the question is, what the hell, guys? I mean, everything is fine exactly the way the physics predicted it. Did he get shocked? Maybe emotionally, but not electrically.
A man from Colorado was lucky not to be electrocuted.
Are you kidding? As far as physics is concerned, he's not supposed to get electrocuted. It has nothing to do with law. He's inside.
The outer surface of his car took
This guy's a storm chaser. So his camera was running.
the hit, blowing out his tires as the
Tires didn't help.
lightning sliced through his car and into the ground.
What happened was that it hit the radio antenna. It used
Antenna got vaporized.
to be right here. The antenna going up about that high.
If you find yourself driving
And I love their conclusion. All right, guys, this is the sort of stuff that you could write for the Science Channel,
through a lightning
History
storm,
Channel, or History Channel today. If you're an English major, and if you have zero understanding of physics.
pull over and keep your hands on your lap. Don't touch metal like the steering wheel or the radio.
Was he touching metal like the steering wheel when he was driving? Yeah, he was, right? Did he get shocked? No. Pulling over?
That
a
way,
lightning storm. If you pull over or if you stop driving in the middle of a lightning storm, if I'm behind you guys, if the traffic comes to a stop or slow down, I would come after you with a baseball bat. All right? Just keep driving. Being inside a car is just about to be the safest place where you could be during a lightning storm.
you'll survive this.
You will survive that 100% of the time because you're inside a car.
The monster created by a man they called Mad is turned loose to strike terror into the hearts of men.
Austin Richards is a self-described mad scientist. But tonight, he's going to play both Dr. Frankenstein and the monster at the same time. He plans to zap himself with 2 million volts of electricity, protected only by a homemade metal suit.
I've really been obsessed with the idea of being a mad scientist. The mad scientist knows exactly what he's doing, but at the same time, there's sort of an element of unpredictability to what he's doing. Sometimes it gets out of hand.
Austin's interest in current events began when he was 14 years old. For a Halloween show, he built what's known as a Tesla coil, a machine that shoots fiery bolts of electricity through the air.
And that first Tesla coil made sparks that were about 12 inches long.
Tonight, Austin is unveiling his latest creation, 2 giant Tesla coils that can fire 2 million volts over 20 feet. But he isn't satisfied with just watching this dangerous light show. He wants to be part of it. Austin knows he could never survive a direct hit from the giant coils without some sort of protection. So he designed a special suit made of metal that would transform him into a human lightning rod. The idea for the suit first came to him at a restaurant, and he quickly scribbled his original design on a napkin. Eager to bring his creation to life, he went shopping for parts at the local hardware store.
So I started selecting bits and pieces of heating duct and dryer duct, actually trying them on my body, slipping them on my arms and legs, and I got some interesting comments from some of the people that work there.
That makeshift suit has now evolved into this, makeshift suit. And though he may not make any best dressed lists, Austin hopes his suit will protect him from a 2 million volt direct hit.
What we're going to try is something that's never been tried before, which is to create almost, in a sense, double jeopardy, having 2 Tesla coils, suffusing a whole area with electricity, and I'm going to put myself right in the middle of it.
Austin has invited a select group of guests to witness this terrifying experiment. Are they going to see an electrifying performance or an electrocution? Austin begins by displaying the awesome power of the giant Tesla coils. He holds up a block of wood. It bursts into flames, but he's shielded by his protective glove. So far, so good. Next, Austin ups the stakes by raising up a solid steel wrench. It's bombarded by a barrage of bolts, but he's still okay. Now he's going to step right into this electrical storm and subject himself to 2 million volts of white-hot lightning. This scientist must be mad. If Austin's homemade suit should fail, he could be fried to a crisp.
If I haven't done my safety check properly, I could die.
He cautiously moves into position. The coils surge to life. Millions of volts of raw power pound his body.
The shocked onlookers can't believe what they're seeing. It only takes 100 volts to kill someone. So how could Austin survive 2 million? Incredibly, he's done it. Austin's electrifying experiment is a success.
I was really hoping that it was going to work, in the sense that I was really hoping I wasn't going to get killed or injured. And I remember feeling a really deep sense of relief when the arcs began hitting him. I didn't feel a thing.
Beaming with success, Austin lights a cigar to celebrate. His crazy homemade suit actually works. Maybe this mad scientist isn't so
If you knew that you were about to be struck by lightning, and if you were to jump, would that prevent you from getting struck?
mad after all.
No, right? So which means that you don't need to be grounded. Which means that you don't need to be touching the ground. So the excess charge is going to reside outside of the metal container. The electric field inside the conductor is going to be zero. So you got this conducting material. So within the enclosure, the electric field is zero. So what that means is that any conductor is going to shield any charge within it from electric field created outside the conductor. What that means is if you have any sort of sensitive electronics that needs to be protected from any accidental sparks from outside so that it doesn't get fried, you have to place them inside a metallic enclosure. Hence the reason why all the sensitive electronics are usually housed inside metallic enclosures.
When a thunderstorm forms, people's lives can be at risk.
We tell people when thunder roars, go indoors. What we mean is seek a safer shelter.
If you're ever caught out in a thunderstorm, one of the safest places to be is in a closed vehicle.
Many people believe the rubber tires on a car will keep them safe, but that's not true. It's the car's metal body that provides protection, as this high-voltage experiment will demonstrate. A Tesla coil is the lightning simulator, an electrical transformer that discharges 750,000 volts of electricity, more than enough to kill. Dr. Lisa Lazarek is an electrical engineer who's willing to sit in a car underneath the coil to prove that the metal body will protect her.
The electrical charge striking this car is going to conduct around the outside surface of the enclosed body, so I should be fine as long as I don't touch the metal of the car. But it's one thing to talk about the theory, and it's another thing to put it into practice. So I guess I'm ready.
The electrical charge flows around the metal body of the car and discharges harmlessly to the ground.
I'm fine. The theory has worked as expected. My feet are slightly tingling, and because I was nervous, my hands are still clamped together. But other than that, I'm fine.
All right, so what's wrong with the explanation that you provided?
Outside surface of the enclosed body, so I should be fine as long as I don't touch the metal of the car.
You can touch the metal of the car, you're still fine, because you're inside the metallic enclosure. The strength of the electric field on the inside is zero, and the electric field is what drives the charges across your body. If there's no electric field, there's no chance that you're gonna get yourself electrocuted. Okay, next question. Once the charge is outside, the lightning is gonna strike, and then it's gonna deposit light charges onto the metal surface, right? What is the component of the electric field which is gonna be parallel to the surface? If it's a static distribution, guys, which means that charges are not moving, right? Along the surface, charges stop moving. The reason why the charges stop moving is because the net force acting on each and every single charge is going to be zero, which means that the component of the electric field, which is parallel to the surface, is going to be zero. That's what it means on each and every single charge. Or else you would have currents on the surface. So the only surviving component on the surface is going to be the component which is perpendicular to the field. All right, and so which means that the only component which is going to survive is going to be the component right on the surface. Notice that the charges will not be uniformly distributed if the surface is not smooth. Notice that the charge concentration is going to be much higher around sharp edges and the pointed corners. Is that making sense? So the shape is going to matter. Sharper the edges are, the higher the charge concentration is, which means that charge density is going to be large. The strength of the electric field is going to be large.
All iron witness to man question. How can I prove it?
Knowing this about electricity, Franklin asks himself one more question. How can this knowledge serve humanity?
It has pleased God in his goodness to mankind to finally show them a way of protecting their buildings from the mischief of thunder and lightning. Take a small iron rod with one end buried 3 feet.
In his almanac of 1753, Franklin reveals the details of his invention. A rod of iron placed on the roof of a building can safely discharge a bolt of lightning down a wire connected into the ground. He doesn't patent the lightning rod. It will be his gift to the world.
The ordinary lightning rod, the Franklin rod, is still the basis of the lightning protection code in every single country in the world. It's still today the best way to protect an ordinary house or a structure from lightning damage.
Calming the odor of lightning, this frightening thing, this had a huge impact on the public imagination. There was an episode, for example, with two ships side by side. One had a lightning rod and one didn't. Both struck by lightning, one destroyed completely. The one with the lightning rod, perfectly fine. First, the clergy felt that he was usurping a prerogative of the Almighty. Franklin said, well, we do not hesitate to protect ourselves from the hail of heaven with roofs and shields, so we should be entitled to do the same with lightning.
In an age of reason, his proof that the lightning discharge is an ordinary natural phenomenon and not a manifestation of the powers of darkness or the force of an angry God was seen as a tremendous blow for reason against superstition.
In 1753, Franklin is awarded the Copley Medal, the 18th century equivalent of the Nobel Prize for Science. This once runaway printer's apprentice is now the most famous American in the world.
This metal attract lightning. All right, you've got the lightning rods on top. All right, so the lightning is missing the Chicago Control Tower. All right, look at these pictures. What do you suppose the size of these lightning bolts are? All right, I'm talking about the diameter or the radius of this thing. Given the fact that you can actually see this miles apart. This picture, the distance between these two buildings, I used to work here, so this is about a mile, and this distance is probably about 10 miles, and look at the size of this. All right, so what do you suppose the size of these bolts are? Lightning bolts are. All right, so we can get a pretty big estimate of that. So let's use the problem number 4 for lightning. So we're going to be looking at the visible portion of the lightning strike. All right, so what do we have? We got the linear charge density for this. All right, it's going to be 10 to the minus 3 coulombs per meter. So it's given to us in terms of a linear charge density. And, oh, I hate this one. Once again, they claim that the air molecules break down, which means that they will just ionize, and an electric field exceeding 3 million newtons per coulomb. If that's the case, guys, the lightning would just light up the entire surface of the Earth. That sort of stuff is crazy. Which means that the entire air would become ionized. All right, so let's go with the assumptions that I'm seeing here. So the electric field strength is going to be 3 million, and the linear density is going to be 10 to the minus 3 coulombs per meter. Okay, so what is the radius of this column that we will be interested in? Lightning. All right, so you got the cloud, you got the ground. So the lightning is going to strike. And we will be taking a look at a small portion of it. You're going to grab a region like this. Just copy it out. And what I'm interested in is the radius of that region. So what I'm going to do, I'm going to make a small circle, which is located right here. And then I'm interested in the radius of that small region. Okay, so I'm recording it. That's what I need. All right, so what's given to us for that region? So R is what we're trying to figure out. Question mark in terms of meters, and maybe express it in terms of feet. I mean, it looks like it could be in terms of inches, but I doubt it. Or else you would not be able to see that from that distance away, from that far away. All right, so linear charge density is given. It's going to be 1,000 coulomb per, what is it, meter? And also the supposed strength of the electric field is given, so this is going to be 3 million. Meters per coulomb. All right, so what is the size of a lightning bolt? What's the thickness of it? That's what we're looking at. What's the radius of the cross-sectional area? The best way to do it is just turn this region into a Gaussian region. So in green that you're looking at, this is going to be my Gaussian. Okay, so I created my artificial Gaussian region. Now everything is in green. And then now I should be able to solve this problem just fine. Okay, so I listed everything that we need, and then let's move forward. There's going to be a net charge here. All right, so within that Gaussian region, the flux of the Gaussian region is going to depend on the strength of the electric field intercepted by the area of the Gaussian. It depends on the net charge from the inside. All right, so here's our generic expression. All right, so we will be looking at the electric field coming out sideways, which means that the area is going to be also parallel to it. So I'm going to rewrite this. All right, so this area that we're looking at is a cylinder. All right, because it is a cylinder, we know that the area of a cylinder is going to be the circumference times the height or the length that we're looking at. All right, we're only interested in the area of the Gaussian, which is going to intercept the electric field. So that's going to be the area which is the underside that you're looking at. All right, so we'll do a back substitution, meaning that this is going to get substituted back into this. The strength of the electric field is assumed constant, so it's taken out outside of the integral. So we got 2 pi RL divided times E, net charge within the column itself, divided by epsilon naught. All right, solve for R. All right, so when you solve this for R, this is what you end up getting. You have 2 pi. I got my constants here. Right from there, keep my constants there. 2 pi, and then you have E. You got your L, and you have your E. All right, so at this point, I'm going to check to see what I have. Check to see if I'm done. All right, so we got a value for E, which is good. So it's going to go here. And epsilon naught, this is a constant looking up. Pi is a constant looking up. All right, do we have a value for Q? Oh, no, shit. Do we have a value for L? L would be the length of the column that you're looking at. I don't know what my Q is. I don't know what my L is. So what do? And we want L. L is not given. Instead, this is what they give us. Okay, what is this represent?
Well, another formula.
We have, yeah, you use the formula for linear charge density.
Okay, which is? All right, so this formula that you guys, I like the way you guys go, oh, we get a formula, man. You guys are still thinking in terms of formulas. Think of in terms of concepts, which can be expressed in terms of formulas. What is the linear charge density? It's the net charge along a line, right? All right, so this is the net charge along the column of this lightning bolt that you're looking at. So in essence, you got what you need. You don't have the individual values for this, but you have a collective value. So what that means is you got a value for this divided by that, right? All right, so we got that. So here's what we know. Since Q divided by L is your charge density, okay, because of the fact that that's this divided by that is your charge density, then we got everything we need. All right, so this is going to be lambda divided by 2 pi epsilon divided by E. Okay, now we got everything we need. All right, so we got a value for this. This is going to be 3 million. We got a value for this. This is going to be 10 to the minus 3 coulombs per meter. You plug your numbers in, and then you will get yourself a number. What is it, 20 feet or something? What is the radius?
Overcoming
So, metals, do they attract light?
damaging effects of one lightning strike can be hard enough, but a few rare individuals, like Park Ranger Roy Sullivan, are proof that lightning can strike twice and more. His daughter remembers his first strike.
This is from the first one. That's in 42, and lightning went through his watch. And see, it has a hole through side to side.
For 27 years after this first strike, Roy was untroubled by lightning until one fateful day in 1969. A side flash bounced into his truck, hitting him in the neck and burning his head.
So, can you be struck by lightning while driving? Yes or no?
Yeah, yes. Your windows open.
If your windows, absolutely, yeah. So roll up your windows, guys. Roll up your windows. More than likely, you're not going to take a direct hit. It's usually a side flash. Side flash is usually survivable, obviously. All right. So
by lightning
Just roll out the windows. So the streamers from your body is not connecting to separators from the phone.
Till one fateful day in 1969. A side flash bounced into his truck, hitting him in the neck and burning his head. The odds against Roy being struck a third time were over a quadrillion to 1, but only a year later, near his home, lightning hit a transformer and arced to his left shoulder. But this was not the end. In 1972, while taking refuge from a storm inside a mountain station, Roy Sullivan was singled out for a fourth time.
I recall Roy having lost all of his hair on his head. He also had a burn around his ankle that was, I would consider, substantial.
Come on, Rick. How are you, Roy? Pretty good. Working at law today? Sure am. Have a good one. Too.
By 1973, Roy had taken to carrying a bucket of water with him when he made his rounds, in case he caught fire again. Even though he tried outrunning the thunderstorms, in June 1976, Roy was struck again for a record 6th time. And his troubles weren't over yet. The following year, while out fishing, Roy was struck for the 7th time, and he became known as the Human Lightning Rod.
How many of you guys seen the movie The Curious Case of Benjamin Button? And those of you guys who have, remember the guy in the movie who always kept talking about getting struck by lightning, and every time he would talk about it, the story was completely different. And he got struck 7 times in the movie. So it's loosely based on this guy's life.
People called him that before, human lightning conductor, but I don't know. I don't know if it was a chemical mineral in his body. He said that before.
Roy was worried that metal on his body might be attracting the lightning.
He didn't even wear a wedding ring or a watch because of that. He didn't wear those.
Belt buckles and metal zips fuse and melt after a lightning strike, and many lightning survivors have terrible burns from metal objects that they were holding or wearing. But does metal on the body actually attract lightning?
All right, so what's the electric field within the Gaussian surface if the net charge resides on the outside? All right, guys, if the net charge resides on the outside, so what is the flux of the Gaussian in this case? If the net charge on the outside, what happens to the net charge on the inside is going to be 0. So if the net charge is 0, the Gaussian, the flux is going to be 0. All right, that's it. So it's 0. Give yourself 2 points for that. All right, where does the extra charge reside on a metal? Extra charge, excess charge.
On the outside?
Okay, before we get back to that. So what's the net charge inside a Gaussian surface? If there's equal number of positive and negative charges on the inside. So if you have,
0 as well.
It would be 0 as well, right? If you have equal number of positive and negative charges, the net charge is going to be 0. All right, so if you have equal number of positive and negative charges, when you add them up, it's going to be 0. All right, so that's what happens. All right, so extra charge on a metal is going to reside right at the surface, right? Okay, so the question is why? Come up with a justification as to why the excess charge has to reside right at the surface. When we are dealing with excess charge, we are dealing with like charges, right? Like positive or negative charges. So if that's the case, what happens between the like charges?
You're going to repel each other, and the surface is going to be like as far away from each other as they can spread out, probably.
All right, so they will repel each other to the surface, and they will get repelled as far away from each other as possible, right? So surface is the furthest that they could get to. All right, so I'll give you 5 points for that one. All right, so we had a discussion about this. These are usually test questions because I want you to be able to justify these. So we were talking about commercial airplanes. On average, they get hit twice by lightning. So the passengers on the inside will remain safe. So why is it that the passengers on the inside will remain perfectly safe from the lightning?
Well,
all right. Okay, go ahead.
I'll say, well, the plane just kind of acts as like a giant car, I guess you can say, with like the same way how it protects. It's just like a car, but amplitude in size by like a couple, like 100 times. So it's the same principle as why if you're safe in a car, you're safe in a plane, just a giant metal flying box. So.
All right, so I'm going to give you 5 points, Bailey. What I'm looking for, if this were a test question, and obviously it's going to be a test question because this is the sort of stuff I ask you guys, usually. Number one is metallic enclosure, right? Okay, so a couple of things that I'm looking for. I may repeat some of the questions on every single test, but I'm repeating a question, which means that I'm also looking for something more than before. Okay, so let me get back to what it is that I'm looking for. So at least when you guys have this question on the test, you know how to answer. Number one, if it's a metallic enclosure, when lightning strikes, it's going to deposit same like charges onto the metallic enclosure. All right, I'm going to make this a metallic enclosure. This is your airplane or UFO or whatever. All right, so the lightning comes in and then boom, zoom, and then just zaps it. So imagine that the negative charges are being deposited. All right, so what happens to the negative charges, the like charges, like negative charges, immediately they will be repelled to the surface. All right, so surface is going to become negative charge. Okay, this I'm going to indicate as a negative net charge. That's what you're looking at. So that negative net charge is going to get dispersed, distributed onto the surface. Okay. Okay. So once that's the case, because the like charge is the furthest that they can repel is going to be the surface. So the question is this: why would you be safe while you're on the inside? The reason why you're going to be safe on the inside is because of the lack of electric field on the inside, right? So how do we know that the electric field on the inside is going to be zero? We know that because what I'm going to do is I'm going to place my Gaussian right here. All right, so blue is going to be my Gaussian, right where the surface is, right inside the surface of the metal. And then what we will do is we're going to take a look at the electric field on the inside. All right, so flux, that's the amount of electric field intercepted by this area. So I'm looking at the area of this Gaussian. It depends on the net charge on the inside, right? All right, so solve for E. When you solve for E, there's the expression that you come up with. Okay, cool. So this represents the net charge on the inside. And what is the net charge on the inside? Net charge on the inside is going to be zero, right? All right, because the net charge on the inside is zero, the electric field on the inside is going to be zero. Okay, so what does that mean? What that means is if the electric field on the inside is zero, which it is, all right, and your body has charges on it, obviously. Okay, so the absence of the electric field, there would be no force acting on the charges making up your body. All right, there's no way you could get electrocuted under the circumstances because the net electric field is zero means that the charges on your body will not accelerate through your body. That's what it means. Okay, so you're going to be perfectly safe. So I'm looking for two explanations from the previous test. I didn't get a chance to grade the previous test yet, the conceptual portion. All right, everything is graded out of 2 points. Okay, so the reason why you would be safe in the previous test is because the like charges will be repelled to the surface. So that's the full explanation. And they would remain at the surface. While you're on the inside, there's no way for these charges to be able to get inside of the metal. But the second explanation is, and that's the explanation I'm looking for, because this is a metallic enclosure, and inside the metallic enclosure, the electric field is going to be zero. The reason why the electric field is going to be zero because the net charge inside is going to be zero. All right, so that's the explanation I'm looking for, or I will be looking for, more like it, on the test. All right, so number 6 is taken care of. Or for the exact same reason, the person inside the car. Okay, so this is in regards to the car. A woman gets trapped inside a car. So there's a down power line, remains in contact with the metal casing of the car, which means that the metal casing of the car is already part of the circuit. If you walk up to this car and put your hand on it, more than likely it will kill you. All right, it's a dangerous situation. So she's inside the car, she's touching the metal inside. She can also touch the metal on the outside. So the question is, why is she safe? Guys, she's gonna be safe for exactly the same reason, believe it or not. What is the net electric field on the inside? All right, so the current is composed of like charges, electrons. So they will remain outside of the car. All right, despite the fact that she's on the inside, the electric field on the inside is zero. Got it? She can touch the metal on the outside. None of these charges will be forced to go through her body. That's the reason why she can touch the inside, she's fine. She can touch the outside of the metal, she's still fine. That would be the short answer. All right, but there is a little bit more to it than that we will discuss. So this is more of a setup for the next lecture. So she can touch the inside of the metal, she's fine, because the electric field, there's no net electric field on the inside. So there's no electrostatic force field on the inside that would push the charges through her body. All right, so, okay, now that we've been discussing it for a while, for the past 5 minutes, what is the strength of the electric field inside a conductor? And explain why. Why the strength of the electric field inside a conductor is going to be zero, because the net charge within it is zero. The net charge would reside outside, not inside, because the net charge of the like charges would be repelled to the surface. And inside a conductor, the net charge has to be zero. There's no, because the charges are free to move, and the furthest that they're going to be able to move is to the surface of the metal. All right, so that's it. So go ahead.
Is that why if you open the window, that's a problem? Because the air is charged and it charges the air inside your car and then it wants to flow through you. Is that why that's an issue?
Oh, Matthew, are we talking about lightning?
Yeah.
Okay, just hold that thought briefly. Okay. No, that's not the reason why, but that's it. Good enough. I like the way you're looking at. Hold on. Let's discuss this shortly. All right, so what's the strength of the electric field on the inside? It's going to be zero, so we're good with it. Okay, going back to what Matthew was saying. Matthew, give yourself 5 points. What's the best place to be during a lightning storm? I would take a metallic enclosure over just about anything else, 100% of the time. I would much rather be inside an airplane or inside a car, and with my windows up. Okay, so the question that Matthew is asking is a good one. Why is it that you have to have your windows up? Okay, this would be a nice test question, actually. Now that I'm thinking about it. You need to have your windows up, and here's the reason why. Lightning phenomenon. Let's get back to it. All right, so bottom of the clouds will be negatively charged. And the Earth gets polarized and becomes positively charged. And then you have these step leaders coming down in high concentrations. All right, so these are your step leaders. And then you got these positive charges going up. All right, so these are known as the streamers. All right, I just want to change color here because there's a bit of bullshittery that goes on here that I need to emphasize. I'm making it look really, really simple. All right, so these are your streamers. Those are the positive charges coming out of the ground. And then we got the step leaders. Okay, this one is actually fairly accurate. So you got the step leaders. So what happens when they make connection, they end up getting a discharge, which is the opposite of an ionization that you're looking at, streamers. Okay. The problem happens when the streamers from your body makes connection with these step leaders. Okay, you want to avoid that. And how do you avoid that? Glass is going to work just fine. All right, so if you put glass in between, what happens? The glass is going to get polarized and that takes time. Okay, you don't want the streamers from your body become connected to the step leaders. You don't want that kind of connection, so you just want to separate that. All right, so that's the reason why you have to you just put a barrier between yourself and the step leaders. Okay, and in something like glass would be perfectly fine for you to be able to separate that connection. Okay, this is kind of unrelated. This is something that we're going to keep going back to, though. Negative charges coming from the clouds. These are negatively charged ions, or these are electrons coming from the clouds. That's what we got. So the bunch of them coming down. So it's going to these are going to be the step leaders that you're looking at. But I want you to remember. I want you to notice that the ground is positively charged because of polarization. These positive charges coming from the ground are ions. So the question is, where are we getting these ions from? And positive charges get pulled out of your body as well. So the question is, where are we getting these ions from? There's no explanation for it, guys. The ground being positively charged because of polarization is not the same as generating positive ions. There's no explanation as to how we get these, where we get these positive ions from. Okay, these are like mysteries. How would your body generate these streamers, for example? So that's a question mark. I have no idea. Somehow something happens. And then all of a sudden these positive charges positive ions get pulled out of your body. And then when these streamers start making connection with the step leaders from the clouds, obviously that's when you get struck by lightning. So the question is, how does your body generate these streamers? It's a question mark. All right. So the lightning is a fascinating phenomenon. All right. So Matthew, I'm going to give you 5 more points for that question. So that was an interesting discussion that you got started there. All right. So moving forward, does the strength of the electric field within a capacitor remain constant? There shouldn't be an or. All right. So does the strength of the electric field inside a capacitor remain constant? Okay. Does the strength of the electric field change within a capacitor or remain constant? All right. That's a question that we will answer shortly. All right. We talked about the light, heat, as well as the sound with it lightning. So because the light, quantum jumps, heat, random vibration and rotational motion of the molecules. The sound is the sudden expansion and the collapse of the air, obviously. All right, so does the shape of the tip of the lightning rod matter? Okay, we'll take a look at it. Does the metal on your body attract lightning? All right, so that's the last question is the one. Oh, what is it that I just want to do regarding this problem? Don't want to use numbers, so this is fine. All right, so this problem is related to the understanding of how well you can apply the formula and how correctly can you apply it. All right, I'm talking about the flux formula. Okay, because these are vectors that we're looking at. Okay, let's have a quick conceptual discussion regarding this. Okay, guys, the electric field in this case is going to be from left to right. All right, so here's your electric field going from left to right. This is the electric field. All right, so that's what you got. All right, so it's from left to right. Your area is in the same direction. Okay, so are you going to get a positive flux or a negative flux in this case? All right, E times dA times cosine of 0. Okay, so what is the cosine of 0 in this case? It's going to be 1, right? So this is going to give you a positive flux that you're looking at. Notice that the area vector is in the opposite direction of the electric field. So the electric field is to the right, the area vector is to the left. So E times dA times the cosine of 180 is going to give you a negative flux, right? All right, so here it's entering into the region, so it's going to give you an inflow. Here it's electric field is leaving the region, so it's going to give you an outflow. Inflow is going to be negative, outflow is going to be positive. All right, notice that the area vector is going to be perpendicular to the surface. That's always the case. So area vector is in the vertical direction, and the electric field is in the horizontal direction. So what's the angle in this case? It's going to be 90 degrees. What is the cosine of 90 degrees? It's going to be 0, so there's no flux in that direction, right? All right, so this is more of a conceptual exercise so that you can see how the mathematics is being used. All right, so I didn't want to discuss it yesterday because I was thinking that it's too early to discuss something like that. All right, lightning, the conductor. So we talked about conductors, and we already mentioned that the like charges will be positive or negative. They will be repelled to the surface. So the excess charge is going to remain on the surface, which means that the electric field on the inside is zero because there's no net charge on the inside. So the metallic enclosures is one of the best ways you can protect stuff from electrical discharge, provided that you can place it inside these metallic enclosures. And so that's
Overcome.
So next question is, speaking of metals, are they good at, I mean, we know they're good conductors, but are they really good at attracting lightning?
The damaging effects of one
Does metal on your body attract lightning? Lightning rods are made of
lightning
metal.
strike can be hard enough, but a few rare individuals
And the purpose of the lightning rod
of the skin of the human
wearing. But does metal on the body actually attract lightning? At a high voltage lab in Manchester, England, researchers are preparing to find out.
We use an impulse generator, which is charged to a voltage of approximately 1.5 million volts, causing a simulated lightning bolt. Mannequins have been painted with an electrically conductive paint so that they simulate the resistance of the skin of a human under normal conditions.
Various metal objects have been...
All right, so she's the one who's wearing the metal jewelry. Same height, so height is not a factor.
attached to the test dummy on the left to see if it will be struck by lightning more times than the one on the right.
All right, so he takes the first hit. He takes the second. The third one. And finally. So finally she gets it.
In this tech, the electrical flow.
And now look at his reaction.
Just like a real lightning strike, the electrical flashover has left telltale fractal patterns on the dummy's body. If Roy Sullivan did have any metal on his body, it should have had no effect. Lightning experts believe it was due to a combination of high exposure and bad luck.
Roy Sullivan was outdoors in an area with quite
So metal on your body, does it attract lightning?
a bit of lightning.
It doesn't appear so, right? All right, so the next question is, does the size of the metal matter?
Maybe even more metal. Of course, if your tongue piercing is this...
Because the argument is that the metal on your body is not going to attract lightning because it's too small. So the next question is, if that's the case, how about the size of the metal?
big, lightning is the least of your worries.
So I go into the top of the head and go out to the bolt and back in.
It just goes to show, don't put any really big bolts in your mouth during a thunderstorm.
Finally, a test for the mother of all studs.
Well, cheek piercing there.
It's unlikely to catch on at many nightclubs, though it might just help you get in the door. Will it attract lightning? At last, a direct hit.
Well, that knocked the doorknob right out of his face.
So does the size of the metal matter in terms of attracting lightning? Well, Mythbusters is kind of conclusive on that. So the conclusion is, of course it does, right? So don't have a doorknob on your face. It's a statement to that end. Do you think that's an accurate conclusion? Yes or no?
I'm going to say no.
Okay, Billy, you want to say no. Why? Because you don't like Mythbusters?
No, Mythbusters is a good show. I'm kind of sad.
Oh, it's an awesome show. I love Mythbusters, but I love it for all the wrong reasons.
Yeah.
I love the way they come up with these experiments, but a lot of the times their conclusions are a little bit off. In this case, once again, they are way off. There's a reason for it. It's not the size of the metal that matters. It is the shape of the metal. Okay, do you guys notice that when you have these sharp edges and pointy edges, the charge concentration goes up, charge density goes up. As a result, the strength of the electric field increases. So as a result, it becomes a lot more attractive to lightning. Notice the lightning rods, extremely long and pointy, right? Okay, why use metal? Why not use glass or porcelain or whatever? You end up using metal, and there's a good reason for it, because obviously it's going to get polarized, and charges are free to move much faster up and down. All right, so you can keep increasing the strength of the metal, the strength of the electric field, because as these step leaders start to come down, and the polarization starts to get stronger and stronger and stronger, so it starts to become much more attractive to lightning. So it is the shape of the metal. It's extremely sharp, and it's extremely pointy on purpose. All right, so it looks like this. This is amazing. All right, so that's the design that Franklin came up with, and King George III decided to come up with a spherical ball as a lightning rod. All right, you know, Franklin, when he came up with his own design, he decided not to patent it, so anyone and everyone who wanted to use it could use it, right? And why then King George decided that he was going to come up with his own design? All right, guys, the pointy, sharp is attractive to lightning. When you have a spherical ball, metallic ball, what happens? The charges are uniformly distributed, so the strength of the electric field is not going to be as much, so it's not as attractive to lightning. Got it? So why is it that King George, instead of using Franklin's design, decided to come up with his own, which is not as good? Any ideas?
He was jealous of Franklin and wanted to have an invention of his own.
Who said that?
That was Lucas.
Okay, Lucas, why would you be jealous of Franklin? This guy's the king.
I mean, like, Ben Franklin was pretty smart, pretty successful. You know, had a good life in him. You know, I'd be jealous of him too.
Well, he's one of my heroes, but the other guy's a king.
Yeah, King George was also kind of crazy, so that there's also that.
Well, all kings are kind of crazy, so let's ignore that one. All right, Lucas, I'm going to give you 5 points. All right, King George.
He was mad at us for winning a revolution.
That's exactly right. Matthew, give yourself 10 points. The reason why I've been just talking about Franklin nonstop on a $100 bill, because this guy deserves to be on a $100 bill for everything that he had done. And of course, King George could never forgive Franklin for being such an asshole to him. All right, so the nice thing about King George's design, though, now we know how to protect us from lightning. Okay, for example, your car antenna. Do you guys notice that there's a small ball on top? All right, so King George's design doesn't work, so why not use something that doesn't work? All right, so instead of, if you're going to have metal, you don't want to put anything pointy on it. They put a ball on it on purpose because you don't want to attract lightning to yourself. So Franklin is once again the winner in this argument. King George, not so much. So this is the face of a winner on a $100 bill, and this is the face of a loser. And speaking of losers and winners, oh my God, this is beautiful. All right, guys, so you're looking at a World War I German military helmet. Okay, so what was the purpose of it? All right, so it's a battle. You run out of bullets, so what do? You ram down the enemy. And then there's a lightning storm, and then you're losing a bunch of people, right? So it's not the metal helmet which is a problem. Germans are smart. World War II, they go, okay, let's keep the helmet. Get rid of the spike on top. All right, because it's not the shape, it's the shape of the helmet, the metal that attracts lightning. It's not the size. All right.
In the middle of a children's soccer game, the sky is open. Players take shelter under it.
All right, I don't know if you guys remember
Tree and
umbrellas, the certain umbrellas that they used to have. They used to have these pointy.
Coach puts up a large umbrella. It's a
10, 15 years ago.
terrible mistake.
And that it would attract lightning to yourself. The new ones, the top of the umbrella has a metal piece which is kind of small, and it doesn't have sharp edges usually, so they got rid of it. Now, a lot of people struck by lightning survive because of the simple reason that it's usually not a direct hit. These are cyclones. I don't want to say that these are easy to survive, but these are survivable.
People feel the force of the lightning strike. But how could so many have been hit by a single bolt? Most victims are not hit by lightning directly, but by a charge that jumps from a nearby object, such as a tree. This side flash still has enough power to stop the heart and burn the skin.
Okay, now the ground is going to become electrified. Whatever you do, don't lie down. And there's a good reason for it that you will find out tomorrow. Don't ever lie down on the ground. And keep your legs together.
Victims can also be shocked from below. Immediately after a strike, the ground becomes electrified. The current travels through the person where they make contact with the ground.
Keep your legs together.
Usually,
because the current is going to go up one leg, come down the other.
Up one leg and down the other.
And then your balls are going to get roasted.
If you're caught out of doors in a thunderstorm, the best thing to do is get indoors in a sizable building.
So he says that the best thing to do is get inside a sizable building. I'll say get into a car if you can help it.
If you can't do that, you should get into a metal car.
All right, so he says the sizable building first. If not, it's a metal car.
The car's metal body discharges the current away from the driver and to it.
Never stand under the tallest tree. Try to stay off hills where you're the tallest object.
But you're not totally safe indoors.
If you're indoors, you shouldn't touch anything that's connected to the outside.
All right, don't touch anything connected to the outside, such as what?
Because the lightning could strike that outside and come in, and that includes the telephones with
all right, so don't be on a phone with wires.
Wires. Shouldn't be leaning against the refrigerator.
Don't be getting anything from the fridge.
Shouldn't be near the house plumbing.
Don't be pissing or shitting.
Shouldn't be in the shower.
Don't be in the shower.
Just stay away from everything.
Stay away from everything.
Thing.
Guys, versus a car. You can piss and shit in your car, you're still fine, right? All right, so car is always better.
Amazingly, all 17 victims survived.
All right, so best place to be inside a metallic enclosure. Okay, so this is an insulator. So this is a non-conducting sheet, so it's an insulator. Notice that it's charged, the surface becomes charged. And in this case, it is charged positively, so the electric field is pointing in this direction, the area vector is pointing in the same direction. The electric field is pointing to the left, the area vector is pointing to the left. And the stuff that you guys are looking at, this thing is your Gaussian region, right? So you draw your Gaussian region just like this. All right, so that's what we will do. So we'll do a fast derivation. This derivation is going to be really fast. Gauss's law is just amazingly powerful in terms of computing something like that. It's a simple enough geometry. All right, so here's the insulator. It's a charged disk or some kind of a sheet, and it's going to be positively charged. So this becomes the source of the electric field. So the electric field lines are going to be pointing to the left as well as to the right. And then what else do we have? We also have the area vector pointing in the same direction. All right, so the area vector is a vector which is perpendicular to the area. This is the same as the normal. The surface that we were dealing with in physics 1. All right, so what do we do? In order to figure out the strength of the electric field, what we do is we do a Gaussian. Just look at a certain region. So I'm going to draw my Gaussian here. This is my Gaussian surface. And the only stuff that I'm going to be interested in is the strength of the electric field intercepted by the ends that you're looking at. All right, so you're looking at the area here. You're looking at the area here, and you're looking at the area here. That's intercepting the electric. All right, so let's try to do this. So according to Gaussian, this is what we use. The net charge on the inside is going to be responsible for the electric field. And so what that means is you're looking at the circle here, which says that just integrate it in the counterclockwise direction. So here's my region, so I'm just going to integrate this region that you're looking at in this direction. All right, so there's nothing happening in this region, and there's nothing happening in this region. All right, you have an area vector in this direction that's perpendicular to the electric field, so it's not going to contribute. There's an area vector which is perpendicular to the electric field, it's not going to contribute. Okay, so you can just traverse in this direction. So things start to happen right here. Notice that the electric field and the area vectors are in the same direction. So that's what I'm going to focus on at this point. So E and A represents the magnitude of the area on the right. So I'm dealing with this portion of it. And then nothing is happening in this region for the reasons that I explained. So area, once again, is 90 degrees to the electric field, so it doesn't mean anything. So as I'm traversing it in this direction, I get to this point. Notice that the electric field, as well as the area vectors, are to the left. So I keep on with my summation. So the electric field is to the left. The area is also to the left. So the entire summation, the integral mean summation, is going to equal to the net charge on the inside divided by the epsilon naught. All right, so the net charge is the charge that we are dealing with here. So that's the net charge. Okay, so this is straightforward. Negative times negative is going to be positive. So what do we have? We will have 2 times 3 times A equaling net charge divided by 0. All right, so solve for the strength of the electric field. And when you solve for the strength of the electric field, obviously, you divide both sides by 2 and then A, and that's what we're doing. So the strength of the electric field is going to be Q divided by 2 epsilon naught A. And what does that mean? What that means is the following. So this is the net charge distributed over this area. So what does that represent? It represents the charge density, surface charge density. So the net charge distributed onto the surface area is going to give you the surface charge density. All right, so do a back substitution. And we are done. That's it. Straightforward, it's easy math, easy work. All right, so this is the strength of the electric field of a charged insulating sheet. All right, the mathematics is straightforward, but math is not physics, guys. All right, so math is not physics. All right, so this is how you do the math. Okay, so having said that, here's a really tough question. If it's metal, electric field on the inside is going to be 0, right? All right, can you figure out the strength of the electric field on the outside? All right, so this has to be some kind of a metallic enclosure. That's the reason why the strength of the electric field is 0. Or it could be a piece of metal, it doesn't matter. Inside, the strength of the electric field is going to be 0, so the net charge is going to be on the outside. Okay, so the mathematics is going to be exactly the same as before, so I'm not going to repeat it. I'm just going to cute. All right, so the work is already here. So this is for a non-conductive sheet. All right, so this is the one that we've been discussing. All right, so what we have, so you got the net charge located right here. So this is positive charge, Q that you're looking at. So this is the work that we just did, and this is the result that we came up with. Okay, so what if it's a metal piece? It's a piece of metal. So if it's a piece of metal, what is the electric field strength of this piece of metal? Okay, how do you do that? Oh, I was hoping that I had that. Okay, oh, I have it here. Q. All right, so it's the same idea. All right, so this is a metal piece. Inside, the strength of the electric field is 0. So the net charge is going to be on the outside. So you put your Gaussian right here. And when you place your Gaussian right here, so what you have? When you place your Gaussian right there, all right, so the net charge on the inside is going to be right here. All right, so your net charge is right here. So that net charge is going to be responsible for the electric field in this direction, and the area vector in this direction. Electric field is from left to right. It's in this direction, and then so the area vector here is perpendicular to the electric field, so it's not going to have any contribution. Once again, it's the same rule. You do your integration in this direction, in the counterclockwise direction. You will find the contribution only within this region. So notice that within this region, you have the strength of the electric field times the area. That's what gives you a flux. And here's the net charge on the inside. All right, so isolate E from here. When you do that, this is the formula that you come up with. Q divided by A is going to be your surface charge density. And here's the formula that you come up with. Surface charge density divided by epsilon naught is going to be the strength of the electric field of a charged metal. That's it. The weird thing is if it's a flat surface just like this one is, notice that this is a flat surface, the charges will be uniformly distributed on the surface. So if it's a flat surface, the charges will be uniformly distributed, which means that the strength of the electric field is going to be constant, only for a flat surface, just like that. All right, so I'm talking about capacitors. Here's what I'm talking about. This is a parallel plate capacitor. Notice that this plate is getting positive charge. You're dealing with a flat surface. This region is flat. So which means that the charges will be uniformly distributed. What that means is the strength of the electric field is going to be uniform. So if this is uniform, if the charges are uniformly distributed, the electric field strength is going to be constant. Got it? So this is your capacitor. And inside a capacitor, the strength of the electric field is going to be constant, provided that you have these flat, smooth surfaces. And that's what you're having. All right, so this is an expression that would come out of math. So the question is, why would the strength of the electric field be constant on these flat surfaces? That would be your test question. Okay, strength of the electric field will be constant if the charges are uniformly distributed, which means that the charges will be equal distances to each other, right? That's what it means. And which means that the strength of the electric field due to these charges parallel to the surface will cancel out. The components of the electric fields parallel to the surface will cancel out. Only surviving component is going to be the perpendicular component. Okay, so the shape of the tip of the lightning rod is going to matter because the sharp edges as well as the pointy edges will have a much larger charge density, right? Okay, so based on the last one that we came up with, what happens to the strength of the electric field when you increase the charge density? When you increase this charge density, what happens to the strength of the electric field? The electric field is going to get stronger, right? So it becomes more attractive. Charge density around the shape, around the sharp edges as well as the tip is going to be much, much, much larger, which means that the tip and the sharp edges tend to be a lot more attractive to lightning because the strength of the electric field is going to go up. The electric field is going to get stronger and stronger near the sharp edges as well as the tip. All right, does not allowing your body to attract lightning? It's not the size of the metal, it's the shape of the metal that may attract lightning. Okay, so you don't want anything which has sharp edges or between the point. So that's what you need to avoid in terms of attracting lightning. Question number 10, does the strength of the electric field change within a capacitor or does it remain constant? Inside a capacitor, charge density is going to be constant on the metal piece as long as it's flat. So which means that the strength of the electric field is going to be constant. All right, it's towards the middle. If these are infinitely big sheets, obviously it's going to be constant all the way through. But because of the fact that these metal plates have finite sizes, around the edges it's not going to be constant, but towards the middle it's going to be fairly constant. But we don't have to worry about that in this class because this is still a freshman level physics. Okay, so this is good enough. All right, so what's left over? There's one more concept left over before we jump into the next discussion. So if the charge distribution is constant, the charges are uniformly distributed, the strength of the electric field is constant. So inside a capacitor, the strength of the electric field is going to remain constant. That's what it means. If the strength of the electric field is constant, then if you place charges here, you're going to experience a constant acceleration, constant force, constant acceleration. So their motions will be uniform. All right. Problem number 6. Okay, so we're looking at the nucleus of the gold man. I don't want to do this numerically, but there's a derivation that I want to use that you will need in solving problems on Sunday. Okay, so this is the last topic that we will get to treat in this one. All right, so what do we have? We got a nucleus atom. It's got a radius. The radius is known. It's 6.2 times 10 minus 15. All right, so that's 10 to the minus 15. So that's the size of the nucleus. It's got a net charge. Z is the number of positive charges of the protons, so it's going to be 79. So the net charge is going to be positive. So it says that to plot the magnitude of the electric field from the center of the gold nucleus outward to a distance of about twice as great. All right, so what happens to the strength of the magnetic field and you start to plot it from the center of the nucleus all the way to the outside, almost twice the distance of its original radius. That's what it is. All right, assume that the nucleus is spherical and the charge is distributed uniformly throughout the volume. All right, so how do you do a problem like this? All right, so let's come up with a nucleus. Okay, so case number one is the first one that I'm going to look at. This is going to have a nucleus, so R is going to represent the nucleus of this. Okay, so we've got a uniform charge distribution on the inside. So assume that this is uniformly distributed, so the net charge is going to be on the inside. The first thing I'm going to do is, this is case number one, I'm going to place my Gaussian on the outside. So I'm going to place my Gaussian right here at a radial distance of lowercase r. That's where it's going to be. So I'm going to mention that in my case number one, R is going to be larger than capital R. So what I'm interested in is the strength of the electric field outside of this region. So that's what we're going to figure out. So what is the strength of the electric field in this region? Remember, the net charge on the inside is going to be positive, so that positive charge is going to be responsible for generating the electric field. All right, so the electric field is going to be radiating away from the nucleus. That's what it is. All right, so how do we do this? The case number one is kind of straightforward, and that's the reason why I picked that one. This is more of a warm-up. So strength of the electric field times the total area of the sphere that you're looking at. So this is for a sphere, is going to depend on the net charge on the inside divided by epsilon. All right, so we know something about the area of a sphere. All right, so it's a nice symmetry. So the area of a sphere that we get to use is going to be, what is it, 4 pi r squared. All right, one of the things that you guys will struggle if this is a new concept for you, and it is, I want you to notice that this r is always the r for the area. Then this, you're always dealing with the area of the Gauss. All right, so don't get them confused. All right, this capital R is the radius of, this is the radius of the nucleus, and lowercase r is always going to be the Gaussian. Right, in this case, it's going to be fairly clean, but in the next case, if you're not careful, things can go to hell. A lot of students get confused about that. All right, so that's back substitution. It gets back substituted. Now what do we have? So now we got 4 pi r squared. All right, and then you got the strength of the electric field. So net charge divided by epsilon naught, and this is going to give us an expression that we're looking for. So divide both sides by 4 pi r squared. All right, so by dividing both sides by 4 pi r squared. All right, so you got your cancellations. These are going to cancel, and then we're done. All right, so we got our expression. So what do we have? Net charge divided by 4 pi epsilon. All right, and then your variable is going to be r, so this is going to be r squared. All right, so this is outside of the region, so immediately I can graph this. All right, so now we are outside of the radius. So here's the strength of your electric field. It's a function of r, and this is your radial distance. So on the outside, what you end up getting is you got this inverse relationship. All right, E is going to be inversely related to r squared. So what that means is electric field strength is going to decay inversely. Right? So outside, that's what you end up getting. All right, so this one was easy. All right, so which means that the nucleus is going to act like a point charge if you're looking at it from outside. Okay, case gets slightly complicated. When I say slightly, I mean slightly. All right, if you're not careful, you will get confused because of the symbols. The reality of it is this is straightforward math. All right, so case number 2. Now what we'll do is we will go into the nucleus, and then we'll take a look at what happens. All right, so case number 2. Okay, so this is my nucleus. One more time. All right, so this is the size of the nucleus. So what I'm going to do this time is I'm going to place my Gaussian on the inside because I want to see what happens on the inside as I'm increasing the distance, radial distance from the center all the way to the edges. So this is the distance that I'm going to keep increasing. Okay, so R is going to locate the Gaussian surface one more time. All right, so this is our case number 2. And in the case number 2, R is going to be smaller than the radius. And then we will be looking at the strength of the electric field on the inside. All right, once again, the mathematics is the same as before. Okay, so net charge is once again fixed. But, okay, so, okay, now the stuff that I need to clarify. Q naught is going to be the net charge inside the Gaussian. Okay, that's what we're going to be focusing on. So the only difference between the previous one, this one was the net charge inside, this one was the net charge inside the nucleus. All right, so this is the net charge inside the nucleus. This is the net charge inside the nucleus. Here, Q prime is the net charge inside the Gaussian. All right, so before we forget, let me just clarify that. So when you guys go back and refer back to your lecture notes, you'll remember. So this is the net charge that we're looking at inside the Gaussian. All right, so you need to make that distinction. So this is the net charge inside the Gaussian. So the net charge inside the Gaussian, in this case, I'm going to use blue. All right, strength of the electric field is going to change as you start to increase the area of the Gaussian. That's what it means. All right, so the strength of the electric field is going to depend on this radial distance that you're looking at. All right, I'm using R prime there. Maybe I shouldn't. So let's use R. All right, so R is good. Let's use R. Okay. So R is going to vary. All right, so now let's go back and finish up the problem. All right, once again, flux is going to be caused by, flux by definition is the amount of electrical field intercepted by area of the Gaussian. And that's going to depend on the net charge within the Gaussian surface, which is Q prime divided by epsilon. All right, and once again, we were dealing with spheres. And once again, we're using a symmetrical geometry. For a sphere, it's always going to be 4 pi r squared. All right, so this is the area of the Gaussian once again. It's going to be intercepting the electric field. All right, we'll do a back substitution. And isolate E from here. And when we isolate E, the equations will look identical. Ooh. All right, and then I will stop right at this point. All right, this is as far as we're to get. So, all right, so this equation looks like this equation. All right, so both these equations look the same. All right. They look alike, except there's a slight difference. All right, so just want to get in this region. All right, so what's the difference? Okay, guys, what's the difference between these two equations? The difference is this. This is the net charge. This is the net charge inside the Gaussian. This is the net charge of the nucleus. This is the net charge inside the Gaussian. All right, so what you need to do is you need to express the net charge inside the Gaussian surface in terms of the net charge inside the nucleus. Got it? In order to get the complete expression. So this net charge inside the Gaussian needs to be expressed in terms of the net charge of the nucleus. All right, mathematically, I'm going to do a little bit of mathematical bullshit thing. What we need to do is we need to express the net charge inside the Gaussian in terms of the net charge of the nucleus. So the net charge inside the Gaussian, which is this, has to be a function of the net charge. And then you need to plug this into that. So how do we figure out the net charge inside the Gaussian in terms of the total net charge? What do we do? Any suggestions? All right, so how do we express the net charge inside the Gaussian in terms of the total charge? Okay, guys, the only way you could do that is if you remember the assumption. What is the assumption? Assumption is the assumption that I underlined before. Charge density should be uniform. All right, or else good luck solving this one. So the volume charge density has to be uniform. All right, so with this assumption in place, default, yeah, you can solve this one. This is a huge assumption. All right, so I want you to remember this assumption. So the charges are uniformly distributed. If the charges are uniformly distributed, I love doing this. And now you can solve this problem. All right, so if the charges are uniformly distributed, then you can solve this problem. All right, so what do we know? Charge density means the net charge divided by the volume. All right, so V here is the volume. All right, so this is the volume of the sphere. So that's the net charge. So the charge density of the volume of the nucleus has to be the same as the charge density within the volume of the Gaussian region. Gaussian. Got it? All right, so the volume of a sphere, regardless. What is the volume of a sphere? The volume of a sphere is going to be 4 pi r cubed divided by 3. All right, so here's a generic expression for it. So what we will do is just slide the generic expression here. Okay, so, all right, so here's the generic expression, so just apply it to both of them. All right, so that's what we will do. Okay, so what I'm going to do is I'm going to grab this term and then isolate Q naught. That's what I'm going to do. So here's the active quotient of the formula. All right, so let's grab Q naught, Q prime from it, and then simplify it. All right, so Q prime, in this case, is going to be Q divided by V prime divided by V. All right. Now write out the expression. V prime is the this is the volume, so this is going to be 4 pi r Q divided by 3. And V is the volume of 4 pi r cubed. Okay, so capital V is the volume of the. All right, the rest is kind of straightforward at this point. Right, we cancel. And then what do we have left? So we come up with an expression for Q prime, which is going to be r cubed divided by the cube of the radius. And then here, right, and then right, so let's substitute everything with that. Okay, so this is going to get substituted. This gets substituted here. And as soon as we do that, we're done. All right, so strength of the electric field is a function of the radial distance. This would be your expression K, the strength of the electric field. And Q prime is going to be expressed in terms of Q, so I'm going to place my Q here. And what do we have? We have R squared, and then we have R to the third power, and then we have, all right, I lost connection on that. So immediately, we got our cancellations. This is the third power, this is the second power. Right. So you get your cancellations. So I'm going to move this here, and as a result, what do we have? So this and these will cancel, and that's it, we're done. So its strength of the electric field as a radial distance is going to be Q divided by 4 pi epsilon naught divided by r cubed, and then you have your R. So what that means is, within the radius of a sphere, strength of the electric field is going to increase radially. That's it. So you increase the radius, this goes up, the strength of the electric field is going to go up. All right, so what that means is, if we copy this, come up with an expression. So all the way up to the radius. All right, so this expression means that the strength of the electric field is going to be directly proportional to the radial distance, so this thing's going to go up just like that, and then it's going to diminish the square of the radius. All right, so that's it. Inside, it just increases the electric. So inside the electric field is going to be directly proportional to the radial distance. Okay, guys, that's it.